Hello, I've had a question in Unit 1, Lesson 3 about relative motion, looking at number 27. So number 27 is the cruise ship sailing north at a speed of 10 kilometers per hour. So just to give ourselves a bit of a graph here to visualize this, up is north. So we are moving at 10 kilometers per hour, which I'm going to change to meters per second because I see later in the question we're using meters per second. So if we divide that out, I get 2.8, let's call it 2.8 meters per second north. All right, a passenger walks along the deck with a velocity of 0.5 meters per second toward the stern of the ship. She then turns toward port and walks to the railing. So on a test, I'm not going to use stern and port because I'm not a sailor. So anyway, for those that don't know, stern is the back of the ship. So she's walking to the back of the ship at 0.5 meters per second. And then, so I'll put stage 1, and then stage 2, she turns toward port. Port is left. I remember that because port has 3 or 4 letters, and so does left. And she goes at the same speed. So that's stage 2. All right, so probably the nautical terms are causing headaches here. I don't use that. I use front, back, left, and right. Anyway, okay. So what is her velocity relative to the ship? So what I do to help myself out, here is my ship. Here is the person walking. So if I am on the ship, so this means that I am standing right here watching. Yes, I am a stick man. I am watching. I see her moving 0.5 meters per second toward the back of the ship. So that's what I see, because when it says relative to, that's where I draw me. So I'm relative to the ship, so that means I'm on the ship. So she is moving at 0.5 meters per second to the back of the ship. All right. B part. Relative to the water. So here's the boat. Here's me in the water. I hope there's no sharks. All right. And she is moving for both motions. Oh, yeah. Okay, anyway. 0.5 meters per second and 0.5 meters per second. Okay, so let's just finish up A here. I missed the both motions thing. So, a bit of technology, I can move that. Let's shrink that down a bit. So the other one then, she is moving at 0.5 meters per second to port. All right. And again, because I'm on the boat, that's what I see. Now, if I'm in the water, watching the boat go by, so what do I see? I see the boat heading that direction, heading, so let's call it north, since that's what it said. And she's moving south. So for the first part, relative velocity would be, so we see 2.8 meters per second, so that's my boat. All right, it's heading north. And then plus 0.5 meters per second south. All right, so that's in the relative formula, VA plus VB. Direction's important because 2.8 I'm going to leave as a positive, north is positive, but now it's south, so it's subtracting. So if I'm sitting in the water watching this person go by, I'm seeing her traveling at 2.3 meters per second north. All right. The second one, now she's moving out of plane, so it's no longer one-dimensional, it's now two-dimensional. So what I have to now do is I have to do my stacked addition. All right. So velocity of the boat. Velocity of the boat is not moving left or right. Plus, because it's two-dimensional, so I'm treating it like a vector, plus 2.8 J heading up north. Plus, how is she walking? She's walking left or west, so negative 0.5 I, but she's not moving north or south, so it'd be 0. So the relative velocity then, vrel, would be negative 0.5I plus 2.8. Okay. The magnitude of the velocity, relative, is the square root of negative 0.5 squared plus 2.8 squared. And I get 0.5 squared plus the 2.8 squared, square rooted, 2.84 meters per second. Her angle, tan inverse of 2.8, the y component over the x component. So shift tan 2.8 divided by 0.5. And that looks like, let's call it 80 degrees. All right, so therefore, she is moving 2.84 meters per second. Going back to my equation, it's negative, so it looks like she's heading west, 80 degrees, that's a positive, so north. So from the water, if I couldn't see the boat, so if I was holding my hand up blocking what I see, I can just see her head, for example, it would look like she's moving at 2.84 meters per second west, 80 degrees north. So there's how you handle a V relative. So it's easy if it's one-dimensional or you're in the same frame. So an A part, it's easy because I'm on the boat. I'm just watching this person walk around. When I'm in the water, this is when it becomes a little bit more challenging. Question I part, this is one-dimensional, so I can just add and subtract the vectors as I please, but make sure when you go two-dimensional, as soon as you get off that plane or that line, now you have to start doing that stacked vector addition again. Hopefully that helps with the question. If you have any other questions or follow-ups, let me know, and I'll do what I can to help.